Welcome. In this video, we'll walk through a detailed solution to a problem involving the determinant of a matrix equation. Our objective is to solve the following equation for real numbers x. The equation involves the product of two 4x4 determinants, and the product equals 0. The fundamental property of real numbers tells us that if a product of two numbers is 0, then at least one of those numbers must be 0. Applying this to our problem, it means either the first determinant, let's call it delta 1, is equal to 0, or the second determinant, delta 2, is equal to 0. So, we have two separate problems to solve. Let's begin by tackling the first determinant. To simplify our work, we'll use a standard substitution. Let's set a equal to e to the power of x, and b equal to e. Remember, since x is a real number, a will be a positive real number. Now, we can rewrite our determinant using these new variables. Notice the third row has e to the 2x, which is the same as e to the x squared, or a squared. Similarly, the fourth row has a to the fourth. This determinant is known as a Cauchy matrix, or more precisely, a generalized Vandermonde-style determinant. There's a known formula for its value, but for our purposes, we'll follow the method of row and column operations as outlined in the solution. The first step is to manipulate the columns to introduce some zeros, which will make expansion easier. We'll replace the second column with C2 minus C1, and the fourth column with C4 minus C3. This simplifies to the determinant you see here. The first and third rows have become much simpler, which is exactly what we want. This simplifies to the determinant you see here. The first and third rows have become much simpler, which is exactly what we want. Now that we have zeros in the first and third columns, we can expand our determinant. Expanding along the first row is a good strategy. The expansion looks like this. We only need to consider the first and third terms, since the second and fourth terms will be multiplied by 0. Let's perform some column operations on the 3x3 determinants. These operations are often key to making determinants more manageable. For the first determinant, we'll replace the third column with C3 minus b times C1, and for the second, we'll use C2 minus 1 over a times C1. Notice that the new C3 and C2 columns are now proportional to the original C1 column, which will simplify things immensely. After these operations, our determinant simplifies to this expression. This is a common strategy, performing operations to reveal proportionality between columns or rows, which makes the determinant 0. And there we have it. The first determinant is 0. So, our analysis of delta 1 is complete. This means the condition delta 1 equals 0 gives us the solutions to the entire equation. We've established that delta 1 equals 0. So now, our task is to solve the equation delta 1 equals 0 for x. Let's use the second method presented in the solution, which provides a factorization of the determinant. The general formula for this type of determinant, known as a Vandermonde determinant, is given by the product of all possible differences of its variables. While our determinant isn't exactly this, it's closely related. Its value can be factored. We are given the factorization of our first determinant, delta 1, as shown here. Let's analyze it. To find the solutions, we need to find the values of a and b that make this entire expression equal to 0. A product is 0 if and only if one or more of its factors are 0. So, we set each factor equal to 0. Let's solve each of these conditions. Remember, our goal is to find values for x. The first condition is a squared equals 1. Since a is positive, remember a equals e to the x, the only real solution is a equals 1. Substituting back a equals e to the x, we get e to the x equals 1. Taking the natural logarithm of both sides gives us our first solution, x equals 0. The second condition is b squared equals 1. Again, b equals e, which is positive, so we must have b equals 1. However, b is defined as e, which is approximately 2.718, so b cannot equal 1. This condition yields no solutions. The third condition is b minus a equals 0, which means a equals b. Substituting back, we get e to the x equals e. This directly gives us our second solution, x equals 1. The fourth condition is a times b equals 1. This means e to the x times e equals 1. Using the rules of exponents, this simplifies to e to the power of x plus 1 equals 1. Again, taking the natural logarithm of both sides, we find that x plus 1 equals 0, giving us our third solution, x equals minus 1. Let's quickly verify our solutions. This is an important step to build confidence in our answer. We found three potential solutions: x equals 0, x equals 1, and x equals minus 1. The problem asks for all real numbers x, so we should check that these values indeed satisfy the original equation. Our condition for delta 1 to be 0 was equivalent to a equals 1, or a equals b, or a times b equals 1. Let's see if our solutions fulfill this. When x equals 0, a equals e to the 0, which is 1. This matches our first condition, a equals 1. When x equals 1, a equals e to the 1, which is e. This matches our second condition, a equals b, since b was defined as e. When x equals minus 1, a equals e to the minus 1, then a times b is e to the minus 1 times e, which equals 1. This satisfies our third condition, ab equals 1. All three of our solutions satisfy the conditions we derived. Therefore, we can be confident that these are the correct solutions. So, we have successfully solved the equation. We started with a product of two determinants, set it to 0, and saw that one of them, delta 1, was 0 for our solutions. We then solved the equation delta 1 equals 0. A quick note about the second determinant, delta 2. The solution provided uses a similar, extensive calculation for delta 2. However, there's a much faster way to show it's redundant. Notice that the expression for delta 2 is identical to the expression for delta 1, with one crucial difference. The third row of delta 1 involves a squared, b squared, and so on, while the third row of delta 2 involves a cubed, b cubed, etc. Because the structure is the same, if there were solutions for delta 2 equals 0 that were not solutions for delta 1 equals 0, the problem would be much more complex. The provided solution shows that delta 2 also factors in a way that leads to the same roots. A equals 1, a equals b, or ab equals 1. This means solving delta 2 equals 0 gives the exact same set of solutions. Therefore, our solutions from delta 1, which are x equals 0, x equals 1, and x equals minus 1, are the complete and final set of solutions for the entire equation. Thank you for watching.